How do I get out of this? All right. Boom.
Hi, everyone. Welcome to this Earth-to-Earth seminar. So thank you for joining us today on the 25th of February. So as a reminder, the mission of Earth2Earth is to engage the UK geosciences community with inspiring science from internationally leading researchers to promote inclusivity and diversity, support early career researchers, and highlight geochemists' contributions to addressing global environmental challenges. And this program is open for all UK institutions to participate in. So for questions, please use the Q&A channel at the bottom of your Zoom window, and these can be posted at any time during the seminars. And we'll have 10 minutes at the end for me to relay your questions to the speakers. And so now we get to the nice bit. It's my great pleasure to introduce today's speakers. We're fortunate today to be joined by Dr. Jabrane Labidi and Dr. James Dottin. Jabrane holds a permanent CNRS position at IPGP Paris, and his work has involved investigating the origins of the evolution of volatiles in the Earth and the terrestrial planets using the stable isotopes and isotopologues of volatile elements. James is currently a postdoc at the University of Maryland, where he is measuring and evaluating the causes of sulfur isotope variations in ocean island basalts with a view to understanding deep mantle volatile evolution. So in our first talk today, Jabrane will be discussing the origin of mantle nitrogen, and James will then present his recent sulfur isotope work. So take it away.
All right, thank you so much, Helen. Let me know if you can hear me actually. Right, okay, thank you so much. I would like to also extend my thanks to Oliver and everyone that's actually in the organization board of this great opportunity for me and James to present some of our data. So today I'm going to be talking about the perspective of some of the new constraints brought by the new isotopologue systematics that could be called nitrogen clumped in natural fluids. James and I actually are both interested in this idea of what is the origin of volatile elements. In the case of this presentation today, I will be talking only about nitrogen, which is an extreme volatile element that's partitioned into the atmosphere of the planet, and that's essential to drive the habitability of the planet. So nitrogen is present in the atmosphere, which we breathe, but also occurs in small amounts, but measurable amounts in the Earth's mantle. And it's not clear how nitrogen got there. Basically, what we like to show in geochemistry presentations is pictures of exploding planets to represent how the accretion of the terrestrial planets, especially the Earth, is thought to feature high energy events, collisions, destruction, bulk planet melting, etc. All events that are thought to lead to the loss of volatiles from a terrestrial planet. So it's not clear how volatiles got in the mantle to begin with, and it's not clear in terms of a nitrogen budget as well. Typically for the Earth, geochemists have put together explanations associated with geodynamics. This is here a cartoon of modern plate tectonics on Earth that is thought to potentially redistribute volatile phases from the surface that is enriched in volatiles back down to the mantle, the deep mantle, via subduction. So there's an actual possibility that mantle nitrogen actually derives from their surface. Typically, as a geochemist, we like to think these processes and questions in terms of flux analysis. So there's multiple flux to consider to describe whether nitrogen may be redistributed between the surface and the deep earth. And one of these fluxes is mob degassing, which corresponds to the degassing of the convective mantle. We are also in the need to be looking at plume degassing. But today I will mostly talk about these two last arrows, arc degassing and subduction. The current literature leads us to think that the subduction flux is dominating all nitrogen fluxes. The arc outgassing flux is substantial, but it's lower than the main subduction flux, which lets the community think reach a consensus to the idea that the nitrogen is currently being regassed inside the mantle from air. So air is experiencing a nitrogen depletion, and nitrogen is being brought back to the mantle in some ways via subduction. In today's talk, I would like to talk about new constraints on the role of subduction for nitrogen, and constraints coming from the nitrogen isotopologue systematics. Today, I will be talking about not the full subduction fluxes and the full outgassing fluxes that have been determined elsewhere. I will be talking mostly about a case study, the Central American subduction zone, which is relatively well studied. It's supposed to be a warm subduction zone with even evidence for slab melting in some regions. And it's well characterized for a number of volcanoes across the arc, from Guatemala all the way down to Panama. Here is the original hypothesis for the nitrogen flux in this subduction zone. Basically here, what you have to look at is the pink boxes that represent what we think the fluxes may be for nitrogen based on rock chemistry and gaseous chemistry. We think the subduction flux of nitrogen appears to be twice as high as the degassed flux. Please note that these fluxes are given in the literature with no uncertainties. So they have to be taken with caution. Usually they are considered to represent or illustrate a case of an imbalance between subduction and degassing, which would suggest that nitrogen can indeed be subducted in the deep mantle. The question I would like to ask today, and I'll try to investigate, is how well do we know the outgassing flux, and can we reevaluate it with new isotopic techniques? What we do in this field is to look at volatiles that are associated with magmatic degassing, and we constrain the composition of magmatic degassing in order to say something about the fluxes. What we want, isotope geochemists that live in the lab and that do not go on the field, is to send our colleagues, volcanologists, send them on the field and get those gases that I'm showing here as an example from the eruption of the Santa Ana in Salvador in 2005. Obviously, these gases are interesting illustrations of what the magma and the mantle source might contain in terms of volatiles, but obviously these are, for safety reasons, rarely sampled or never sampled in, I think, the history of mankind. So what we are left to study with are hydrothermal samples. So here is an example of a picture from the POAS. I'm sorry, I did not put the picture credit. It is elsewhere in the presentation, I think. This is a picture from a Costa Rican volcano that has a well-developed crater lake that corresponds to the accumulation of hydrothermal fluids on top of that volcano. From these kind of volcanoes, which are not in active eruption, we can still get some interesting information on the volatile fluxes because there are fumaroles. These fluids are extremely hot, 250 degrees C sometimes. This is the case in one of the fumaroles in that one crater I'm just showing in the picture earlier. But these fluids are full of water. And this water is not always fully volcanic. Actually, a good fraction of that water is just rainwater that has been accumulated in the hydrothermal system in the subsurface. So the question becomes, in this final erupted fluid, what is the fraction of gases that actually come from the melt? And what is the fraction of gas that actually comes from air that's brought in the system by the rainwater itself? For nitrogen, this might be a problem. How much of the nitrogen in the fumarole is air derived? In order to answer that question, we use a new technique associated with the Panorama instrument that's on campus at UCLA that is the largest gaseous source mass spectrometer that exists on the market currently. And the specific geometry of that instrument allows us to not only measure the single isotope substitution, which is the conventional 15 and 14N, which I will be talking about, but it also allows us to measure the unique doubly substituted isotopologue 15 and 15N, which a lot of the colleagues in the community would call the nitrogen clump. This is the one slide with technical aspect. I promise I will not be too boring with that, but this is for the mass spectrometry enthusiasts that may be in the audience. This is showing two mass scans, one mass scan for two different masses, for two different beams on the instrument. I would like you to look at the blue scan, which corresponds to the mass 30, which is the mass that we are looking at, because we're measuring the amount of 15 and 15N, which is on mass 30. You can see the mass spread on the x-axis is extremely small, and the peaks are rather vertical. This reflects a mass resolving power of 55,000. Just to give an idea, this is about 5 times the mass resolving power of a Neptune on a good day when the Neptune is on the high resolution mode. It's roughly about 5 times, a little less than 5 times actually. So we can, thanks to this high resolution, we can resolve 15 and 15N, which is here from the everlasting isobaric interference 14 and 16O plus that exists in all mass spectrometer. This is thanks to this instrument, we can actually access to a flat peak of 15 and 15N and make a reliable isotope measurement. So the reason why we are interested in making this measurement is as follows. We think, so here on the x-axis, I'm showing temperature of a gas, and I'm plotting this against the big delta 30, which is the abundance of 15 and 15N in any natural gas, right? This is here, there's no data in this plot, it's only an equilibrium prediction. This is where we expect any nitrogen from degassing of melt to cracking of organic matter to fall. However, air has been recognized in 2017 by the UCLA group to host a massive out of equilibrium 15 and 15N enrichment. The reason behind that enrichment is not extremely well understood, but details can be found in that original publication. The reason also of this enrichment is almost beyond the point of this presentation. Here, we are only going to use the enrichment as an isotopic tracer to look at how much nitrogen from air is in a natural fluid. So here is the first plot of data. And this is almost the only plot I will be using in this presentation. Here I am plotting in the x-axis, the conventional little delta 15N, which is a representation of the amount of 15 and 14N. On the y-axis, though, I'm showing this new measurement, big delta 15 and 15N, or big delta 30, which is the same thing, which corresponds to the amount of 15 and 15N in a given natural sample. You can see in gray and in yellow samples from natural hydrothermal samples and air standouts. So the yellow points here correspond to air standouts. There's multiple features that need to be described on this plot. One of them is that there's a huge variability in natural sample on the x-axis, which is known, which is not new, but also on the y-axis, which has been unrecognized so far. The yellow points, I will say before I go on in this talk, the yellow points correspond to air standouts. So they define what the air value, the air composition on the y-axis is, and it shows how disequilibrated the values is. But it also shows the external reproducibility of the techniques here. There's about 11 standouts in this one plot, and that give an idea of how reproducible the measurement appears to be. It actually is. It's not just an appearance. Actually, is true reproducibility. So the first observation, I mean, there's many observations that can be made. I think order 0 observation is for a lot of samples that have a delta 15N of 0 that looks like air. In fact, you can have the full range of air contribution. You can be looking at a sample that has a delta 15N of 0 that's fully air, would be around here, or you can be looking at a sample that's about halfway contaminated by air, or a sample that's virtually does not host any air. So what that means is delta 15N by itself is not always very easy to use without the added dimension of the big delta 15, the big delta 30, sorry. Before I go on, I'd like to just break down this data set in a way that's a little more meaningful in 3 types of samples. Today, I will be only talking about the blue samples, which correspond to hydrothermal gases on volcanoes. But you see that the orange and red samples are a little different. They show much less air contamination. I will not be talking about them today. My point is to say that samples associated with hydrothermalism, they can have extreme variation in terms of nitrogen concentration coming from air. So that's something that's going to be a problem, but also interesting in this presentation. So air cannot be quantified with delta 15N alone. Well, that was something that was interesting. So in this presentation, the rationale is to identify nitrogen that comes from air that is assigned to nitrogen with a signature similar to air in terms of the y-axis, and disambiguate this nitrogen from deep magmatic nitrogen that is associated with a value at the origin on the y-axis. Right, that's the rationale of this presentation. So here I'm showing the results, same plot, big delta 30 on the y-axis, little delta 15N on the x-axis. And I'm showing the result for 17 samples that come from the Central American arc. They come from a number of volcanoes, and they come also from a number of hot springs that are on volcanoes. So there's interesting aspects of this data set. Some of them are, for example, that, we see the same sort of pattern than with the full data set, which means that there's a lot of air that is involved in the making of those samples, in those mixed gases. These mixed gases host a large amount of air. None of the mixed gases trend towards the mob composition that's here, which is not necessarily surprising. We're in a subduction zone. There's no reason to really see a lot of mob signatures, but that's an interesting observation. And when you break down this data set, this time in terms of volcanic origin, you start seeing some strange and interesting patterns. One of them being obviously that the Powassan samples, which are the samples that come from this volcano in blue in Costa Rica, they all have a unique trend. All other samples, more or less, are showing a mixing relationship between air and some deep component that is probably associated with the specifics of the slab-derived components here. But for POAS, we're seeing this unique trend that seems to be trending towards an atmospheric component that has a non-air delta 15N. We attribute this unique signature to a fractionated air component. We think that this is a critical observation, because this shows that negative delta 15N in samples that are apparently on volcanoes associated with volcanic activity in some sort, this negative delta 15N may not represent mob nitrogen at all. They may completely reflect the contribution of fractionated air that somehow experienced isotope fractionation in the system. The way we think about this potential isotope fractionation is along 3 different steps that I'm illustrating with this extremely simplified, extraordinarily simplified cartoons. We think that the first step is simply the infiltration of rainwater in the system. And this rainwater brings a substantial amount of air components, because the rainwater is saturated with air in terms of nitrogen and noble gases, which is already known. This is already known for like systematics associated with heavy noble gases, for example. In a second step, this water is warmed, is heated by the volcanic activity that's underneath. This leads water to reach boiling conditions and degassing of water, which is known to be associated with nitrogen isotope fractionation based on the experimental literature. We think that this is this water degassing process that leads air-derived nitrogen to modify its isotopic composition. And the third step is when a geologist, in a dry season, goes on the field and captures a sample that has been fractionated by ongoing water degassing in the subsurface. So we think there's a nitrogen isotope fractionation that has not been recognized before, and that attends the processes of water gas fractionations in hydrothermal systems. Just a few words to say that this is not unique to POAS. In fact, this is a figure here that is extracted from a recent publication that we were lucky enough to publish in Nature last year that shows the delta 15N and big delta 30 of samples from Iceland, Yellowstone, Hawaii, and Ethiopia. And they all show components in their signature that indicate they received fractionated air as well, which we think was caused by the same process, in a process of fractionation of in hydrothermal systems. So anyways, in this POAS volcano, which I'm showing another picture here, the same crater as usual, where you now start seeing some primordial activity, we think there's some fractionation happening in the subsurface, which may explain the composition of that atmospheric component. Now, what's also interesting is, it looks like the high temperature components are distinct at POAS from elsewhere. And that is somewhat surprising because the slab-derived nitrogen in this subduction zone has been well characterized by Longley and Babou, and Lee and Babou in 2005, but also by Vincent Bugini in 2019. We know that the slab nitrogen in this area is at about +5 per mil, and it's not that variable. So it's not clear how to explain the composition at POAS. Well, there's one way to explain it, is that we cannot exclude that the fractionation that modified the isotope ratios in air also affected the magmatic fluids. That we think would mean that air and magmatic fluids are mixed, and then the mixed gas experiences degassing and isotopic fractionation, such that we can actually reproduce this type of signatures. Well, that means that the delta 15N systematics has limitations, obviously, which is not necessarily brand new, but this is a firm confirmation that the delta 15N systematics may be deceiving and provide ambiguous responses when it's used alone. So what can we bring, though, from this data? I still have something like 9 minutes. What can we bring, though, from taking this new data to constrain what was the original hypothesis? What we know is that there's a bunch of air-derived nitrogen in the fumaroles. What does it tell us in terms of the genuine volcanic nitrogen flux coming out of these volcanoes? Well, it's very hard. On a figure like this, what we could do would be to, for example, calculate the average value of air contamination, and somehow prorate the bulk nitrogen flux to this number to obtain the magmatic, purely volcanic nitrogen flux. That's one way to do it. However, is it really valid to do this with our sample set, given the small amount of samples? How can we be sure that these samples have a real representativity to the variable fluxes with time, with seasons, and the various volcanic pulses that occur in Central America, that are known to occur often in Central America? It's probably a risky way to constrain the question. What we do actually, instead of just using the raw data, we turn to nitrogen-helium ratios. Here I'm showing a plot that features on the y-axis big delta 30 values, and on the x-axis you see the nitrogen-helium 3 ratios. We care about the nitrogen-helium 3 ratios for multiple reasons. One of them is that helium-3 is not easily recycled in the mantle. So observing variation of the nitrogen-helium 3 ratio of any mantle source might give you an idea of how much recycled nitrogen might be contributing to this mantle source. So when you look at the previous data, you see the plumes data here. That this comes from the Yellowstone in Iceland. These are the data that show that any mixing relationship between air and a mantle gas in nature will cause these curved mixing relationships. This is just the nature of this plot. The way the plot is constructed is such that there's going to be mixing curves, which is not necessarily a bad thing, because the curves are almost, they are subvertical in the region where the mantle contributions are the higher, which means that we can somewhat confidently extrapolate the trends to determine, the nitrogen, helium, and member value of any given mantle source on any given volcanic region. At least that's what we hope. When we plot the Central American data in the same space, we see, in fact, that all the data converge towards a unique nitrogen helium-3 ratio that's at about 100 million. That means there's 100 million times more N2 than helium-3 in the sub-arc mantle sources underneath the Central American volcanoes. That's about 100 times more than in any other mantle source like a mob source or plume source, which illustrates a substantial nitrogen addition to the mantle source of apparently all these volcanoes. Now that's interesting because we do know the helium-3 flux out of Central American volcanoes. So knowing the nitrogen helium-3 flux allows us to recalculate the nitrogen outgassing flux. And in fact, using the variation of data that actually can explain the distribution and the scatter of our data, we are coming out with a degassed nitrogen flux, a range of values, which actually are between 1 to 3, roughly, times 10 to the 10 gram nitrogen per year. This actually is not different given the relatively substantial uncertainty. This is actually not different from the subduction nitrogen flux in this subduction zone. So what is here, I'll just summarize. This is almost my last slide, which is good. So James, you're gonna have a good amount of time to talk about sulfur. But my point here was to just summarize what we think we have found thanks to this new systematic. We knew that the subduction nitrogen flux was at about 1.5 times 10 to the 10 gram of nitrogen per year. This is coming from the rock literature, the rock geologists. This flux, unfortunately, is given with no uncertainty, but we know that this is about the amount of nitrogen that's subducted every year across this arc. This nitrogen is lost from the slab, partially or totally, to the mantle wedge. And it comes out, the fluxing produces melts that seem to be associated with nitrogen helium-3 ratios of about 2 orders of magnitude higher than the average mantle. That gives us an idea of the degassed nitrogen flux that we find is similar to the subduction flux. What this means is the flux data when nitrogen flux are constrained with nitrogen helium ratios and big delta 30. These flux data actually do not require nitrogen subduction in the deep mantle in this one subduction zone. We obviously cannot extrapolate that to all the subduction zones because the Central American subduction zone is relatively unique. It's very hot, and there's even a slab melting here and there. So the gradient of temperature may prevent to extrapolate these results to all of the subductions on Earth. But this is important to take into account, especially when we look back in time, where hot subduction zones were maybe a little more prominent than they are today. So this is my final slide. I'm just concluding with some of the observations that we made. This picture is, it looks extremely random. It was taken at a protest last year. I was interested also in the 3 last words. Right now, the data that we have is not necessarily enough to understand the full spectrum of the complexity of nitrogen cycling. But what we have learned is that 15 and 15 data are essential to bring new constraints. We have learned that hydrothermalism causes isotopic fractionation. Big delta 30 data does help to disambiguate what are the fractionated components, and it does help to determine what is the true atmospheric contribution in a natural sample for nitrogen. We have found that nitrogen helium-3 ratios can help tracking and quantifying nitrogen subduction in the mantle source. And it appears that the fluxes in this one modern subduction zone do not require nitrogen subduction. And with that, I will perhaps not take questions. I'm waiting for the last part for the questions, and I will just give James his time to give us a nice presentation.
Okay. So I think you have to stop sharing.
Here,
And now I can share. All right, and you guys can hear me? Okay. All right. Well, thank you, Jabrane, for giving us such a nice talk on nitrogen. Now we're going to make a major shift and transition into thinking about sulfur and how we can use sulfur isotope compositions of basalts to identify various mantle sources that are delivered to plume systems. And today I'll be specifically focusing on the plume system associated with the Samoan Islands. So sulfur has 4 stable isotopes, 32, 33, 34, and 36. And we can use the ratios of these isotopes in order to evaluate mass-dependent processes, which is graphically shown as this mass-dependent fractionation line here. And we can also use the ratios of the isotopes in order to evaluate mass-independent processes, which is a deviation from this mass-dependent fractionation line, and is typically shown using this capital delta 33S notation. And just as a note, this is a different notation than the big delta 30 that Jabrane was showing earlier. One of the important uses of sulfur isotope systematics is in our ability to characterize atmospheric reactions. In 2000, Farquhar et al. Showed that sulfur in sediments in the Archean preserve large mass-independent signals, seen as large variations in cap delta 33S. And as time evolves into the Proterozoic, these mass-independent signatures disappear. And the argument for this dichotomy between Archean and post-Archean materials is that there was photochemistry occurring in Earth's pre-oxygenated atmosphere, and as time evolved and oxygen rose in the atmosphere, ozone in the atmosphere blocked various sulfur-bearing molecules from photochemistry, causing the mass-independent fractionation process to subside. Furthermore, considering that there is a clear dichotomy in isotopic composition between Archean materials and post-Archean materials, we can use cap delta 33S measurements as a tool in identifying various recycled crustal materials, and furthermore to place relative time constraints on subduction onset. We can also use measurements of delta 34S in order to identify specific recycled crustal protoliths. As it appears, the bulk delta 34S composition of various crustal materials are distinct. For example, the lower oceanic crust, which is dominated by hydrothermal sulfides, has an estimated delta 34S composition of around +3 per mil, whereas the upper oceanic crust, which is dominated by biogenic sulfides, has an estimated bulk delta 34S composition of around -6 per mil. And so through our measurements of both mass-dependent and mass-independent tracers, we can use sulfur isotope compositions first as a timestamp for subduction onset, and then also as a fingerprint in identifying various recycled protoliths, and also in determining the fate of sulfur materials as they are cycled through deep earth reservoirs. Today, I'll be focusing on the information that we can receive from ocean island basalts and the processing of sulfur in the deep earth. Ocean island basalts are basaltic rocks that are found on volcanic islands. They're located on oceanic crusts, typically away from tectonic plate boundaries, and they're also normally associated with hotspots. Through the characterization of long-lived radiogenic isotope systems of strontium, neodymium, and lead, it's been argued that ocean island basalts are erupting compositionally distinct mantle components, namely the depleted mantle, high mu, enriched mantle 1, and enriched mantle 2. Today, I'll be focusing specifically on data that we've collected from the Samoan Islands. Samoa preserves the extreme enriched mantle 2 composition, which is seen as extreme 87-86 strontium ratios. And Jackson et al. In 2007 observed that there was a relationship between radiogenic strontium and 143, 144 neodymium, and suggested that this relationship between radiogenic strontium and neodymium was linked to the recycling of upper continental crustal materials into the Samoan mantle plume. Now, in the initial characterization of the sulfur isotope composition of basalts from Samoa, Labidi et al. In 2015 identified positive delta 34S variations that were distinct from the delta 34S composition of South Atlantic mid-ocean ridge basalts. And furthermore, they showed that the sulfur isotope compositions were positively correlated with radiogenic strontium isotope compositions, and suggested that this positive correlation was due to the recycling of sulfur components that are associated with the upper continental crust, with a delta 34S value of around plus 10 per mil. Now, although the Samoan Islands preserve or host the extreme enriched mantle 2 end member, there's lead isotope evidence that the Samoan Islands receive dilute contributions from multiple mantle sources, such as the high mu mantle, enriched mantle 1, and the depleted mantle. There's also lead and helium isotope evidence that the Samoan Islands receive a contribution from the primordial mantle, and this is readily seen as high helium 3-4 ratios. Now, considering that there are multiple dilute contributions from various mantle components, Jackson et al. In 2014 also hypothesized that these contributions are being delivered to specific groups of islands. And because that there are distinct lead isotope compositions associated with specific groups of islands, they argued that the Samoan mantle plume was geochemically zoned, where various distinct mantle components are separated from one another and not well mixed, and are ultimately erupted at specific groups of islands. I'd also like to highlight that work by Mundel et al. In 2017 and also in 2020 have been using short-lived radiogenic isotope systems such as tungsten in order to identify primordial mantle components, where at Samoa they observe basalts with negative mu-182 tungsten isotope compositions that are associated with high helium 3-4 ratios. And they argue that the source of these mu-182 tungsten isotope compositions are attributed to a contribution from a mantle reservoir that fractionated from the silicate mantle within the first 60 million years of Earth's accretion. Now, the details into the specific source of materials that are being entrained into the plume and erupted at Samoa is not necessarily well understood. However, the general argument that Mundel et al. Have been making is that this is a primordial component that is associated with a deep mantle reservoir, such as an ultra-low velocity zone. Now, the goal of my work is to essentially use long and short-lived radiogenic isotope systems, such as tungsten and lead, as proxies in identifying primordial and recycled components, and then to further use sulfur isotope compositions to place constraints on the nature and the relative ages of these materials. Firstly, in order to identify and place constraints on the sulfur isotope composition of the primordial mantle, I analyzed the same samples that were associated with that tungsten versus helium correlation. And what we see is that on plots of cap delta 33S versus mu-182 tungsten, and also cap delta 33S versus helium 3-4, that sulfur preserves relationships with radiogenic tungsten and helium, where the primordial material has a cap delta 33S composition of around 0 per mil, and as the mu-182 tungsten and helium 3-4 ratios evolve towards 0, the cap delta 33S composition evolves to slightly positive values. Now, one of the major observations here is that the primordial sulfur isotope composition is about 0 per mil. And this is a composition that is indistinguishable from estimates of the upper mantle that are made through sulfur isotope measurements from mid-ocean ridge basalts. And considering that there is no difference between the sulfur isotope composition of the primordial mantle and the upper convective mantle, this would suggest that sulfur was likely homogenized early in Earth's history. We can also use the relationship between sulfur and tungsten in order to place constraints on the type of reservoir that's contributing both the primordial sulfur and tungsten. Some candidates may be a large low shear velocity zone or an ultra low velocity zone, like I mentioned earlier. There may be the direct entrainment of core material. There also may be a contribution from a reservoir that's undergone chemical equilibration between the core and the mantle. So here I have plotted some hypothetical models, such as the mixing with an equilibrated mantle source or mixing with material directly entrained from the core. And what we see is that our best fit model is mixing between mixing with a dense basal reservoir, such as an ultra low velocity zone that has a negative mu-182 tungsten isotope composition and is strongly enriched in sulfur concentration with about 20,000 ppm. Now, in order to understand the source of the slightly positive cap delta associated with tungsten and helium isotope compositions around 0, we have to look to other isotope systems, and in plots of cap delta 33s versus lead 206, 204, we again see that sulfur preserves a relationship with lead, where material associated with the primordial component has a cap delta 33s of around 0 per mil. And as the values evolve towards more positive 206, 204 ratios, which is associated with that dilute high mu contribution at Samoa, we see that the cap delta 33s values increase slightly. And in our paper in 2020, we argued that this slightly positive cap delta is due to the influence from recycled sulfur associated with the high mu component. Now, in order to understand the nature of that high mu component, we can look to some of the information that we have collected on the sulfur isotope composition of extreme high mu end members. Here I have plotted data from Mangaia, which is an island in the South Pacific that hosts extreme high mu compositions. These data are shown in black. The circles represent bulk sulfur isotope measurements using conventional gas source mass spectrometry, and the triangles represent secondary ion mass spectrometry on individual sulfide grains from the same basalts. And what we see is that at Mangaia, the sulfur isotope composition or values are heterogeneous in both delta 34s and cap delta 33s. The bulk data show negative delta 34s values and also preserve slightly positive cap delta 33s values. In our paper, in our separate paper in 2020, we show or we argue that the source of the slightly positive cap delta 33s at Mangaia is associated with recycling Proterozoic sulfur into the Mangaia mantle plume. And this is an argument that's based primarily on the magnitude of the signal and also based on relationships between cap delta 36s and cap delta 33s. Furthermore, in Cabral et al. In 2013, they observed negative cap delta 33s values, and they argue that the source of the negative cap delta 33s values is due to the recycling of Archean-related sulfur. And this is an argument that's, again, based primarily on the magnitude of the signal. Now, although there is a dichotomy between the bulk sulfur isotope measurements and measurements made using SIMS techniques, what we're observing here is a mixing of multiple recycled components, where the Archean component is likely a small contribution in the extreme high mu mantle end member, whereas it appears that proterozoic sulfur that's recycled is dominating the recycled sulfur isotope composition in the Mangaia mantle plume. What's interesting is that the recycled high mu sulfur at Samoa, which is shown using these gray data points here, appears to share a common cap delta 33S value that is similar to what is observed using bulk sulfur isotope measurements at Mangaia. Now, again, based on the magnitude of the signal and relationships between cap delta 36S and cap delta 33S, it's likely that this signal is associated with recycled proterozoic sulfur. And furthermore, considering that we observe a commonality in cap delta 33S among high mu at Mangaia and high mu influenced basalts at Samoa, this potentially reflects that there's mixing of high mu related materials in the Pacific LLSVP, which results in a widespread distribution of high mu components across Pacific Ocean Island basalts. Now, one of the interesting uses of the lead isotope tracer is in the ability to establish a distance parameter, where Jackson et al. In 2014 created a distance parameter that shows that as samples move further away from the primordial component, or here he terms it the common component, the lead isotope composition becomes increasingly different from the primordial mantle, and that's due to the contribution of various mantle components to the Samoan mantle plume. We can also use this lead isotope distance parameter in order to assess whether sulfur is also zoned in the Samoan mantle plume. And here we have plotted cap delta 33S versus this lead distance parameter. And what we see is, again, there's a relationship between sulfur and lead, where the samples associated with the common component have a cap delta 33S of around 0 per mil. And as you move further away from the common component materials, the cap delta 33S composition increases. And so this relationship between sulfur and the distance parameter would suggest that sulfur is also geochemically zoned in the Samoan mantle plume, and that this material with the slightly positive cap delta and also negative cap delta 36S is associated with the high mu component that's delivered to a distinct group of islands, specifically here, the Vailalu Island. Now I'd like to transition into discussing the enriched mantle 1 component at Samoa. This is a component that's associated with a different type of volcanism. The data I showed previously were associated with shield stage volcanism, whereas the enriched mantle 1 component is associated with rejuvenated volcanism, which is a type of volcanism that occurs after a period of quiescence after the shield stage. And at Samoa specifically, it's erupting enriched mantle 1 material. Now, the source of the enriched mantle 1 materials is not well understood. And furthermore, how it was delivered to Samoa is poorly constrained since it's not associated with plume volcanism. It's been hypothesized that this material could be linked to a prior passage of the oceanic mantle lithosphere over another plume system, such as the Rarotonga plume system, where the Rarotonga plume would impart a geochemically heterogeneous signal on the mantle lithosphere before it was rafted into the Samoan region. And so in light of this hypothesis, it's possible that sulfur may also have a distinct isotopic composition that's linked to the source of material that alter the oceanic mantle lithosphere before being delivered to Samoa. Before I show any data from the enriched mantle 1 component, I just want to highlight that the extreme EM1 component at Pitcairn has been characterized for sulfur isotopes, and De La Volta et al. In 2016 show that these materials have a negative cap delta 33S value, composition that's associated with the recycling of Archean-related sulfur. And so considering that the extreme EM1 component at Pitcairn has been characterized for sulfur isotopes, we can then ask whether there are links between the materials that are erupted at Pitcairn and the materials that are eventually erupted during rejuvenated volcanism at Samoa. So here I have all of the data that we've collected on Samoa, both from the Labidi et al. In 2015 studies and some of the work that I published in 2020 and also plan to publish soon, where we again see that the high mu related basalts have this distinct cap delta that's slightly positive. The enriched mantle 2 component, primarily characterized by Jabrane, has a cap delta 33s of around 0 per mil. And the rejuvenated basalts, which are these light blue points, have variable cap delta 33s. And for the first time at Samoa, we're showing material with negative cap delta 33s values. Furthermore, in our plots of cap delta 36s versus cap delta 33s, it appears that the rejuvenated basalts are plotting in a distinct field. And so considering that we see not only negative cap delta 33s values, but also that these materials are plotting in a distinct field, it's possible that the sulfur is linked to a separate source. I also have plotted these slopes that are generally linked to our Archean or Proterozoic material. The -1 slope is associated with the Archean material, and the -7 and -15 slopes are post-Archean materials. And it appears that our data from Samoa are most parsimoniously linked to Proterozoic biogenic sulfides. Now, although the cap delta 33s of the rejuvenated basalts is in the same direction as cap delta 33s at Pitcairn, at this time, we cannot unambiguously link the two materials simply based on lead isotopes because there is no relationship between sulfur and lead. However, in light of the hypothesis associated with rejuvenated volcanism presented by Jackson et al. In 2010, it's possible that sulfur was delivered into the deep mantle by a separate subducted slab and eventually upwelled by a separate plume system, such as the Rarotonga plume system. And then that material that was geochemically altered was then rafted into the Samoan region, and subduction at the Tonga Trench eventually had caused plate flexure beneath Samoa, resulting in rejuvenated volcanism. And so here I just want to conclude the cap delta 33s composition of the primordial mantle is indistinguishable from mid-ocean ridge basalts, which would suggest that sulfur was homogenized early in homogenized in the mantle early in Earth's history. We also observed distinct compositional differences among the materials associated with the high mu enriched mantle 1 and enriched mantle 2 materials at Samoa. Furthermore, relationships between sulfur and lead allow us to suggest that the Samoan mantle plume is geochemically zoned relative to recycled sulfur components. And then lastly, rejuvenated volcanism has a distinct isotopic composition that links its material to a separate source, likely biogenic sulfur, from a separate recycled slab component. And with that, I will conclude, and thank you all for letting me speak.
This was great, James. It's slightly vexing that you have 6 questions and I only have 3.
So thank you both very much for 2 absolutely superb talks. It will no doubt not surprise anyone here that we have actually a lot of questions. So I'm going to start, and I'll try and balance between both the seminars here. I'm going to start with questions about isotope systematics. So beginning with a question about, Jabrane, your first talk. Someone is asking, why do stable isotope fractionation processes typically affect delta 15 nitrogen values, but not the cap delta 30? And I realize you've already answered that, but maybe everyone would like to hear it live.
Well, I'll just say a few words very, very briefly, because I'd like to hear James answering some of the great questions that he's getting, although I'm jealous. But anyways, my point, basically the cap delta 30 acts as a mass independent signature. The way it's defined, it does not behave like a little delta. Actually, in the definition of big delta 30, We do measure little delta 30. We normalize it to the stochastic distribution. Normalizing creates a notation that behaves as a mass-independent signature. That is why a mass-dependent process will not change the big delta 30.
That's great, thank you. And now let me just move on quickly, and I'm going to come back with more nitrogen questions, but I saw a few questions actually about cap sulfur isotopes, about what do they, I'm just reading because I have a huge number of questions here, so I'm trying to read as many as possible. What do they particularly convey, James?
So that's a great question. And it just points out that I didn't make this clear. The mantle is generally assumed to be cap delta equal to 0. And so if we see any variations in cap delta 33s, it's likely something that's surface derived, like the atmospherically processed sulfur that we see in the Archean, and also sometimes in biological metabolisms, you can have shifts in cap delta 33. And so we can use specifically cap delta 33 or cap delta 36 to identify surface-derived sulfur that links it to recycled sulfur. And I saw another question about relationships between cap delta 36 and cap delta 33, and that is based on the wide variety of data that's been collected on sediments throughout time on Earth. And there are distinct slopes associated with Archean and Proterozoic material. And so basically, if we are plotting our data in terms of cap delta 36 and cap delta 33, and we are looking for slopes, we can try to place relative time constraints on the source of the recycled material.
That's great, thank you. So now moving back to nitrogen very quickly, there were a few questions about nitrogen storage, both within the slab that I believe you answered online, but also from one of the panelists, a question about if there's known storage of nitrogen in continental crustal rocks.
Thank you for the question. It's not straightforward, but basically nitrogen exists as a gas species, mostly as N2 in air, and as a reduced phase in most of the rock record. So it's basically stored as NH3, NH4 plus, often in substitution with K plus, potassium, in making micas. And obviously it's also present in organic matter as NH4 plus. The behavior of that NH3, NH4 plus in the slab system is very complex. It's a subject of active research. I think Sami Mikhail at St. Andrews has worked on that. I don't want to forget some of the colleagues, but I will just also say Colin Jackson at Tulane also worked on that also from the experimental point of view. The research that we did was just to constrain the resulting ratios, nitrogen to helium ratios. But it is true that understanding the behavior of NH4, NH3, and N2 in the slab components is going to help explaining why these ratios are high or low. So great question for the future.
Thank you very much. So now moving back to sulfur, there have been some fascinating observations, obviously the relationship between the cap sulfur isotope signature and lead isotopes. James, one person is asking, do the lead isotopes suggest an age consistent with the cap sulfur anomaly? Do they provide some support for using lead isotopes to potentially discriminate between Archean and Proterozoic recycling events?
I don't know. It's a great question. I think that, are they referring to like lead isotope model ages of a reservoir? Because I think that's what they're referring to. And I think that that is something that has not been constrained yet. And some of my postdoc at Carnegie next year will be looking at high mu in various reservoirs of different model ages to see if, say, ancient reservoirs host the Archean type material and the younger model aged reservoirs have a different sulfur isotope composition. I think that's an excellent question and is the exact direction that I plan on going.
Thank you.
So I have no answer. I'm sorry, I have no answer.
Well, there are many great questions that don't have answers yet. So moving back to nitrogen now. I mean, again, Jabrane, you mentioned this kind of briefly in your text response to the chat, but do you think you could talk a little bit about the nitrogen to helium isotope composition of both MORBs and plumes? And that potentially links on a little bit to James's work, where we're also looking at plumes and we're thinking about sulfur. Sorry, we're thinking about, well, we are thinking about sulfur, but also about helium and then by inference, tungsten.
Yeah, that is a great question that was asked by someone. MORBs have been described by the work of Bernard Marty, 97, 90, and 99, and by the work of Marc Javois, something like 10 years before, in 91. And they showed consistent numbers for the nitrogen helium-3 ratio at about 3 million, right? Plumes are very poorly constrained. Marty in 2003 was Nicolas Dauphas determined the nitrogen helium-3 ratio of high helium-4 plumes that show extremely high contributions of recycled components that are massively overwhelmed by recycling. For those ones, the nitrogen helium-3 ratio goes really high, up to, I think, 10 to the 8, maybe a little more. But for helium-3 plumes, there is no data other than Yellowstone that I know of. In terms of nitrogen helium-3 ratio. So that was the first time that we found a helium-3 rich mantle source, that we characterized a helium-3 rich mantle source ever. And we found the value, that a value that just looks like MORBs. And we do not know if it's by chance or if it means that something more fundamental in terms of how these two reservoirs may have been receiving similar amounts of recycled nitrogen or maybe no recycled nitrogens at all.
So thank you. So now, I don't know if you want to add to that a little bit, James, with respect to Samoa and sulfur isotopes.
Can you rephrase what the question was that you guys started with?
I believe, gosh, now I'm trying to think about how we started this question.
Basically, how do you quantify the addition of recycled sulfur?
How do I quantify the addition of?
Can we quantify? Yeah. Because I think that was the question for nitrogen. I'm guessing you could try to answer that for sulfur.
Right. So to quantify the addition of recycled sulfur, I think that this is a question that has to go even further back to other isotope systems that allow us to identify how much recycled material is in the source. So if we're thinking about high mu and we say high mu is maybe 50% recycled oceanic crust, then we can take our estimates of those sulfur concentrations of the oceanic crust, both upper and lower, and then then we can do a mass balance characterization. But I will say that it appears that almost every plume system is different, and so we're going to have to continue to do the work on mantle geochemistry and figuring out how much recycled crust is in each plume system, and only then can we really, come up with a flux and an estimate of how much material is put in, and then the people who work on the surface can work on the fluxes out through volcanic degassing.
Well, thank you very much. And thank you both for the extended amount of time you've spent answering questions. So I believe we're kind of coming to the close of this session. So I'd like to thank you both for your fantastic talks. Everyone who's watched the talks, whether directly here or on YouTube, and the other panelists, the people that have asked the questions, with my sincere apologies to anyone whose question I've not yet managed to handle. So I believe that's everything here. Ollie, have I forgotten anything?
No, that's fantastic. We'll be back in 2 weeks' time with the next seminar.
Yes, and I believe that's Chenzhou, is that right?
Yeah, and that's on carbon sequestration.
Okay, so again, thank you. Thanks everyone very much, and stay safe and well.
Bye-bye. Thank you.
Bye-bye.
Bye-bye.